Hi everyone. My name is Mohammed Asad Heather, and the title of my project is SEG DDGAN, which is short for segmentation, denoising, diffusion GAN. So the problem that this project addresses is brain tumor segmentation in 3D MRI data. The image shows a sample from the extracted output where different tumor regions have been segmented. And the data set that I've used for this project is the brain tumor segmentation, or BRATS in short, and the 2021 version of it. So automated tumor segmentation, basically the motivation behind this project is that automated tumor segmentation can help in early detection of cancerous growths, enabling the doctors to provide early intervention. It is much faster and cost effective as compared to manual segmentation. And because of the better visualization, it can help in the medical diagnosis process. It can also provide a very detailed view of the tumor's 3D position in the body, and which can help in different surgical interventions like radiation therapy and chemotherapy. And it can also be used for assessing how the treatment is progressing, like the effectiveness of treatment, and so that doctors can make necessary adjustments. Okay, so this project was mainly a research-based project, and the primary objective was to use a diffusion model-based approach for the segmentation of 3D MRI data. I'll discuss diffusion models in just in the subsequent slide. And the effectiveness of the new model was supposed to be measured using the validation DICE score against state-of-the-art models. And the high-level approach for the project was first selecting a base model, which would basically be the backbone network, and then incorporating the diffusion logic for that network. So basically, this would involve the backbone network to model the reverse denoising process, and I'll get into this in more details. And finally, of course, training and evaluating the results, basically. So first, I decided to go with the volumetric transformer model as the base model, which has a unit style architecture with self and cross attention mechanisms. I discussed its architecture in detail in my presentation previously. Because I went with this because it had some really good results, but unfortunately, the code base for this model had a lot of issues. Like I was not able to set it up properly. I was able to train the model, but for some reason, the testing part of the code was not working. So basically, I had to abandon this volumetric transformer as the backbone. So I decided to go with the Splin unit R model as my backbone network, as it is also one of the state-of-the-art models, and it's very effective for 3D MRI data. It is also a U-shaped network with Swin transformers serving as the encoder, and a CNN-based decoder coupled to the encoder via skip connections at different resolutions of the image. Yeah, so I will quickly add a quick overview of how diffusion models work. So they are basically composed of a forward process and a reverse process. And in the forward process, Gaussian noise is added to the image, and the model basically learns the reverse denoising process to generate new samples. The reverse process is a sequence of discrete steps where each step corresponds to a fixed amount of noise reduction, and the output of each step is then used as the input to the next step, gradually reducing the noise in the image until it's fully denoised. But there are some problems with plain diffusion models. They basically work with the assumption that the reverse process can be modeled by a Gaussian distribution. But for this assumption to hold, the number of steps in the denoising process need to be very large. And because of this, it is very slow. And this is basically summarized in this diagram, which shows that the diffusion models are capable of generating high quality samples with good diversity, but they're not good fast in sampling. So a solution for this was basically introduced by researchers at NVIDIA Lab, which basically introduced a way to train the diffusion model in a similar fashion to a GAN. To understand this architecture, I'll quickly just go over how GANs work. So GANs consist of two networks, a generator and a discriminator, and the generator generates new data samples that resemble the training data, while the discriminator tries to distinguish between the generated samples and real samples from the training data set. So both are competing. So basically both are competing to fool each other. So if the loss of the generator decreases, the loss for the discriminator increases and vice versa. So this is the overall architecture of the denoising diffusion GAN. In the forward process, a pair of noise images is generated from the input image, xt -1 and xt. So xt is then fed to the generator as a conditioning signal to guide the generation process. But the important difference between this model and plain diffusion model is that the Gaussian assumption is not made, and the sampling is not done from pure noise, but from a latent vector z. Due to this, the sampling process is almost 10 times faster, and the required number of denoising steps is also very low, about 4 or 5. And after the generation, x dash t -1 is produced from the generated output, and basically the discriminator's job is to mark this pair as fake and this pair as real. So basically, there's adversarial training going on along with the diffusion process. So inspired from this work, I decided to base my model on it. And in order to use this approach for the segmentation task, I've had to first convert the 2D discriminator to 3D by changing all the convolution operations to work with 3D data. I plugged in the SWIN unit R model as the generator for this task in the output of the model. And since the output of the model is supposed to be a segmentation mask, the segmentation masks are used in place of the images, as was shown previously in the diagram. And the same process is performed for the 3D segmentation mask as was for the images, the 2D images. The 3D MRI scan is also added as an additional conditioning signal to the generator, since we want specific segmentation masks and we just don't want any random ones. And finally, the loss of the generator is also modified to account for the dice loss as well as the adversarial loss. So this is the overall architecture that I implemented, but unfortunately, I don't have any results right now because the model is still training. The training is very slow on the system that I'm currently using. I ran a training over the weekend, but it ran into some memory issues, so I had to start a new training yesterday. So I'm planning on at least training it for 20 epochs and then evaluating the performance on the validation data set. And hopefully, if I get time, I'll be able to tweak some of the parameters to achieve better performance. Yeah. Yeah, these are some of the references for the papers that I've drawn influence from. Thank you.